live stream. Today, I'm joined by Katerina, who is going to present her work on Pell Frischmann's work on Space House. So we're going to deep dive into all the structural elements of the building, and a building that I know very, very well because I've passed it numerous times and looked at it from the outside and thought, what a amazing piece of architecture. But of course, I am biased, being an ex-architect. But I suppose, Katerina, could you just start off just by introducing yourself to the listeners and introducing your background and experience as well?
Yeah, thank you, Dom, for the introduction and for having me on this event. So, hello, everyone. Thank you for being here and welcome to this presentation. Before I begin the presentation, let me share a few words about myself. My name is Katerina Psora. I am a senior structural engineer working at Pell Frischmann in the building's structures team since 2019. Over the past 6 years, I had the opportunity to work on many projects from commercial to residential, both new builds and refurbishments. That said, given my strong involvement with Space House, refurbishment have become my main area of expertise. Today, we'll speak about the deep retrofit of Space House, a brutalist building in the heart of London, a project we have been working on since 2018. Space House was completed in October 2024. And with that, let's dive in. Shall I begin the presentation?
Yeah, let's go.
Yeah, let's go. So, Space House is located in the London borough of Camden, just off the main road of Kingsway near Holborn Tube Station. The existing building consists of three separate structures: a 15-story circular tower block, a rectangular block known as the Kingsway block, and the link bridge that connects the two together at first and second floor levels. Both buildings share a common basement of 2 stories. Each building has a separate concrete raft foundation. Due to stresses due to differential settlement, to avoid those stresses, there is a settlement joints between each raft foundation, so they can move independently. Space House was built in the late 1960s by the developer Harry Hyams. It was originally designed by the respected architect George Mars at Richard Seaford and Partners, who is known for his design of many brutalist buildings across the UK, such as the Centre Point in Tottenham Court Road in London. It's as well close to Space House. Pell Frischmann, back then known as Pells and Partners, were the original structural engineers of the project, which was very useful as we had access to most of the archive structural information. This photo is showing the original building and construction. It is worth mentioning the innovation of Space House at the time. The tower block was one of the first buildings in London to be constructed without scaffolding. This was achieved due to the use of the hybrid precast in situ concrete frame, way before this technique became common practice. This allowed for 1 week floor cycle time during construction, which is even difficult to achieve today. Another key part of this construction was the load-bearing precast cruciform units. I don't know if you can see my mouse, but I'm talking
Yeah.
about these cross units. So they had dual purpose. They acted as the perimeter structural columns and as part of the distinctive facade. In 2015, the building was listed as a Grade 2 listed building before it was purchased by our client, Seaford Land. At this point, I would like to thank the whole project team for making this project a success, especially our client, Seaford Land, and the main contractor, BAM. Before I go on into the details of the project, we should first ask the question, why reuse and redevelop Space House? Firstly, reuse is essential if we want to meet the UK net zero targets. The client's brief for the redevelopment was to create additional value by bringing the building up to the standards of the modern workspace, by increasing the net lettable area, and add value to the building, and the building per square foot in general. The building wanted to celebrate the beauty of Space House by stripping back the dated build-up of the original building and allowing the existing concrete frame to be celebrated. Additionally, the suspending ceilings were removed as the floor to ceiling height was too low, too short, I must say better, and not aligned with the modern working space expectations. The public realm was originally designed to be a car park, and part of it was also a petrol filling station, which was not particularly appealing to the modern office worker. The ground floor was given back to the public as it was completely transformed into a space where people can go to relax and have lunch with an outdoor food market. The basement was originally an underused car parking and a storage space. This was turned into an event space with a generous cycle store, which reflects the requirement of an office of a modern office. There was also an appetite to increase the net lettable area by adding additional floors to the top of its building. So this was something that we needed to explore to the next stage, stage two. In order to achieve the client's brief, we needed to understand the condition of the structure, any residual structural capacity, and the remaining design life to determine its capacity for reuse. This will then determine how we can add value to the building, such as additional internal floor area, without adding a disproportionate amount of cost by strengthening or adding foundations. In this session, I will go through the process that we undertook to assess the existing condition of the structure. To make Space House suitable for modern use, we need to assess the building against a number of structural criteria. First, durability. It is essential to determine the remaining design life of the building. Strength, quite obvious, but it's important to allow us to understand if we have any residual capacity that we need to take advantage of. Fire rating, as it is quite common for modern fire requirements to be much higher than previous requirements. So this is a key aspect. Sustainability and tolerances. We need to remember that concrete structures creep over time, and previous construction tolerances tended to be much higher than modern standards. So surveys as essential to determine things like floor flatness and available headroom, which might differ from the archive drawings. Foundations, we should consider that the building has settled over time and that we might have some differential settlement across the building, which may affect again the levels. In order for us to assess all these key elements, we needed to carry out first a desktop analysis with all the available information we had, and then use this to determine what we needed to verify and surveyed on site. The desktop analysis, alongside the assessment of our site verifications, determined the opportunities we had to reuse the project, and then we provided an informed structural solution to the client. The most important thing in the refurbishment, in any refurbishment project, is to understand the existing structure. I cannot stress enough how important this is. As we were the original engineers of Space House, we were lucky enough to have almost a complete set of archive structural drawings, which was essential to determine the form and understand basically the form and behavior of the existing structure. We also had access to the full set of archive calculations, which gave us the existing load constraints and the original design code, which again was essential to understand how the building was built. Space House was built using the design code CP114, which is a different approach from today's codes. It is a working stress design code which adopts a different philosophy from modern design codes. It basically limits the allowable stresses in structural materials under the unfactored loads. Whereas today we use codes, the limit state design codes, which, yes, we use partially safety factors primarily to the loads and some on the material strengths. So it's quite different between the two. The archive information also allows us to understand the existing structural strengths. Back in the day, a typical concrete strength was about 15 MPa, where Space House, for some elements, they specified around 55 MPa, which is much higher than what you would expect. Ultimately, all this information allow us to carry out our own design strengths, design checks of the structure and take advantage any residual structural capacity. We also produced our 3D models to visualize the structure, which was very helpful to understand how the structure works. After reviewing the archive information, we realized that the existing floor plates consisted of precast pre-stressed ribbed slabs that were made from high alumina cement concrete, known as HSC. HSC was used very frequently back in the 1960s by precasters due to its ability to gain its strength very quickly, resulting into a quicker turnaround in the factory. However, HSC has a number of flaws. Over time, it undergoes a process known as conversion. Conversion is a process where the concrete particles undergo some physical changes and become denser. This leads to the concrete becoming more porous, resulting into a significant reduction of its strength. This process usually takes many years. However, factors such as higher temperature or moisture and high water cement ratios can accelerate this process. Eventually, after a period of years, a stable minimum strength can be achieved. The good news is that the convention of HSC was taken into account into the design codes of the time. Another issue with HSC is that when it's fully converted, the reinforcement has reduced protection corrosion, which means that in exposed conditions, such as when it's outside in roof or in bridges and stuff, significant corrosion may occur over time. This resulted into a number of historic collapses, but most of these occurred when the HSC was in a location that was more likely to be exposed to water, such as roof structures. These collapses led to the material eventually being banned. On Space House, all the units were in internal conditions, so we were not as concerned. However, we still need to verify the condition of the units on site. And after carrying out inspections, we determined that they were generally in very good condition and with very little sign of corrosion of the tendons. The HSC precast floor units were created through a collaboration between Pell Frischmann and Fram Precast Concrete Ltd, and they were given the name Frampel units as a combination of the two companies. Here is a CGI of the tower, which should help you understand to get a better understanding of the form of the Frampel units on its floor. As I mentioned earlier, it is common for the fire modern requirements to be higher than it used to be back in the day. On Space House, the new fire requirement of the office floors was 90 minutes, whereas the archive drawings indicated that it was only designed for 60 minutes. So there are three elements of fire resistance of an element that we needed to satisfy. First, the structural capacity, then the integrity, which means not allowing flames to pass through, and finally the insulation, which relates to limiting the surface temperature on the opposite side of the element. All these needed to be satisfied to consider the slab as providing effective compartmentation between floors and avoiding the spread of fire. The typical way of assessing the structural capacity of an element in the fire condition would be to use the Eurocode tabulated methods, which provide a minimum width and cover requirements. However, it's not possible to justify this with the precast floor units, as they had a very narrow cross-section. The more rigorous 500-degree isotherm method from Eurocode 2 was chosen. This involved calculating the temperature profile of the element and the effective cross-section using the data from the code. We were able to prove that the units would have a sufficient structural capacity and therefore also satisfy the integrity requirement. The other consideration of insulation was achieved through meeting the minimum slab thickness requirements of the Eurocode. This allows us to take into account the thickness of non-combustible floor finishes. So we were able to meet this requirement by including the existing floor screed in the overall slab thickness, which were also verified through site surveys later on. Prior to the building being purchased by our client, we did undertake an initial structural survey to have a general understanding of the condition of the existing structure. However, going into stage 2, we knew that further surveys would be required to give a further detail on this and also verify the archive information that we had. This included rebar scans and breakouts to verify that the archive information matches what was originally built. Also, chloride content and depth of carbonation to assess the current condition and therefore remaining design life of the building. For those who don't know, carbonation is where the concrete absorbs carbon dioxide from the atmosphere and becomes more acidic, providing less corrosion protection to the reinforcement. And finally, material testing, including core crushing and tensile tests to verify the material strengths. So to summarize the finding of the archive information and surveys, we found that the structural frame had a residual capacity to take additional floors. It can also achieve we can also basically achieve the fire rating from 60 to 90 minutes. The carbonation levels were quite low, meaning that there is capacity for extension of design life. As the client had the aspiration to add additional floors to the tower, we did some initial analysis and found that the tower could accommodate 2 additional floors without exceeding the original design loads. This was ideal as it minimized the risk of strengthening of the columns and the walls. The 2-floor extension was also preferred by the planners, so it has been seen as a sweet spot for a vertical extension. Now I'm going to run through some of the structural scheme options that we looked for the vertical extension of tower block. For the additional floors of the tower, we initially looked at lightweight load carbon solutions, such as CLT and glulam. However, when this was presented to the planning committee, they were not considered as matching with the aesthetic of the building, and therefore alternative options were considered. The final proposal of the 2 additional floors of the tower consisted of the exposed concrete frame, matching the aesthetic of the building. The first additional floor was a duplicate floor that replicated the floors below, while the top featured an inset story that provides 360 views around London and generous terrace space, whilst minimizing the visual impact from the ground. Post-tension flat slabs were chosen for the new 16 and 17 floors to achieve the 10-meter main office span, while minimizing the slab thickness to reduce loads and also maximizing the floor-to-ceiling heights to the new floors. One particular challenge imposed by the planning committee was the requirement to replicate the existing precast cruciform units on the facade, alongside the reuse of the existing precast T units at the top. Therefore, we need to satisfy ourselves that this approach was feasible and could be developed in the next stages. As you can imagine, the construction of the tower extension was quite complex, and therefore we produced an indicative construction sequence to assist in the planning process. This was followed by careful coordination between the concrete frame contractor, precast manufacturer, and temporary works engineer to ensure everything went smoothly. The general construction sequence was that first we needed to demolish the existing roof slab and cut and remove the existing T units shown in yellow. Then step 2 would be to drill holes into the existing cruciform units below for the dowel connection. Step 3, install the new cruciform units shown in green. down them into the existing units below, and then cast the new level 16 PT slab. And step 4, install and dowel the existing T units back on top, shown in yellow. And then finally cast the level 70 PT slab. This is an image of the archive drawings of the existing cruciform units, which was extremely helpful in the process of replicating the units. As you can see on the image on the right, health and safety back in the day is very different from what it is today. So these are the drawings of the new precast cruciform units that were produced after careful coordination with the precast manufacturers. On the left is the Pell Frischmann new construction drawing, and on the right is the precast manufacturer production drawing based on our drawing. Here are some images on the precast cruciform units before and after casting. One important aspect for the new cruciform units was that the concrete needed to match the existing finishes of the concrete, the original concrete, and it to be as close as possible. To assist in this process, we undertook petrographic analysis of the concrete samples of the existing units to understand the existing cement content and the mix. The process of matching the existing concrete involved various testing and of the colors and the aggregate sizes until the acceptable match was achieved. In the end, a 10 millimeter aggregate size was chosen. The surface of the new units also had to be grade blasted to achieve a similar surface texture of the existing units. The matching of the concrete finish was very important for the council as well, so they were really involved in the process until the acceptable mix was found. Here are some nice photos from the final cruciform unit being installed. At the bottom of the image on the right, you can see the dowel connection being inserted. Grout connection was chosen on these connections to allow more time for curing. You can also see the precast female couplers in the back of the horizontal arms to enable the connection of the slab. Now I'm going to talk about some of the work we have done regarding net zero and minimizing embodied carbon of the project. At early stages of the project, one of the biggest things we could do is to minimize the embodied carbon was to maximize the retention of the existing structure, which meant minimizing demolition. This meant working with what the existing structure has to offer. We worked with the architect and MEP engineers to choose sensible location for demolition cut lines and slab penetrations that avoided extensive demolition and recasting of the structure. One example is the typical floor of Kingsway block. We originally had quite a large amount of demolition caused by large service rises, and the architect did not want any downstand beams, which meant that we needed to demolish and recast a larger area of slab, as shown in the image on the left. We worked with the team to allocate service risers into more structurally favorable locations to support the slab around. Basically, we used trimming steel to support the slab around those openings, but also we used the existing slab openings when needed. Basically, we managed to avoid significant amount of demolition, as you can see in the comparison of these two drawings, and use whatever building holes were provided already in the building. Throughout our design, we aim to minimize demolition by pushing structural elements to their limits, using their full capacity and proposing alternatives to rebuilding. In this particular example, we were assessing the existing RC's beam capacity to accommodate new core holes for the MEP services for Kingsway levels from 3 to 6 floor. The proposed openings were too large due to the proposed fire stopping detail. which would compromise the beam's structural integrity, as you can see on the image on the left. Instead of demolishing the beams in all 4 floors and replacing them with new steel sections to allow space for the services to pass through, we tried to find solutions to retain those beams. To avoid unnecessary demolition and costly solutions, we asked the MEP engineer if the fire stopping detail could be adjusted to minimize the size of the penetrations, bearing in mind that the concrete beam itself has passive fire resistance. The fire stopping detail was then adjusted, permitting much smaller pipe penetrations through the beam. We suggested different locations to avoid shear links, the main reinforcement and the compression zone of the beam. From the archive drawings, we knew the beam cover, reinforcement, and link spacing. However, we asked the contractor to scan prior coring the holes and place the holes between the shear links and ensure that the existing rebar was not damaged during this process. We used the Concrete Society guidance for this check, which states that a hole with a maximum diameter height over 4, but no more than 150 millimeters, has an insignificant effect in the bending of the section. Then we avoided the compression zone of the beam and checked for the localized shear capacity. As you can see, it is very obvious difference between the penetrations between these two pictures. Solutions like this were used as much as possible in this project. We basically investing in the design process of the project to provide solutions that prevent unnecessary demolition, preserve the existing structure, and ultimately reduce material usage and construction costs. By maximizing the retention of the existing structure and making sure that its residual capacity, making use of the residual capacity, we achieved remarkable reductions in the building embodied carbon. We have carried out a carbon assessment during this process of Space House using our own in-house carbon assessment tool. This is something we do in all over the projects, but in Space House it was very essential and demonstrated how building reuse is vital to minimize embodied carbon. The upfront embodied carbon associated with structural alterations gives an equivalent I-Struct-T rating scores A+. Additionally, the upfront embodied carbons of the building aligns with the LETI 2030 design targets. Overall, the reuse of the existing concrete frame has saved approximately 10,000 tons of embodied carbon and waste materials. Space House set a new standard for the redevelopment of existing historic buildings. The retrofit of Space House focused on preserving its heritage, with over 90% of the existing structure being retained. It has become the first Grade 2 listed building, workspace building in London to achieve a BREEAM outstanding certification, while also operating at net zero carbon, cutting both emissions and running costs to its occupants. Space House brutalist mid-century character has been preserved, while new bespoke technologies have been integrated to ensure energy efficiency in its everyday use. Before I finish this presentation, I would like to take a moment to acknowledge the recognition that Space House has achieved. Space House won the DESIN Awards 2025 in the category Sustainable Renovation of the Year. It has also been awarded bronze in the World's Architecture New Awards in the commercial building categories of 25,000 to 50,000 square meters. It has also been shortlisted in the I-Struct-T Structural Awards 2024 and in 2 categories of BREEAM Awards 2025, the Best Refurbishment Fit Out and the People's Choice Commercial Building Award. To this day, it is the largest listed building in the UK to achieve a BREEAM outstanding rating. And finally, it has won two mix awards, the Inside Out Awards, which celebrates the project with exterior and interior design work seamlessly together, and the Workspace Interior Awards, over 70,000 square feet, which recognize innovation, sustainability, functionality, and creativity. These honors reflect the vision and dedication and collaboration that we have to shape Space House into the landmark that it is today. Thank you so much for listening. I hope this presentation was engaging and that it added value to your learning.
Well, Katerina, thank you so much for presenting that project, multi-award winning project, must I say, as well. But yeah, truly fascinating. Such a good job on that as well. Now, I didn't realize about the Briam award there as well. But goes without saying, anyone listening to this, please follow Pell Frischmann, follow Katerina on LinkedIn, doing some incredible work out there, and also posting about their project wins as well. So please do drop them a follow. But it just goes to say, Katerina, thank you so much for sharing that project.
Thank you, Dom. Thank you for listening, and I hope you found it interesting.
Very much so. Thanks so much. And yeah, thank you for joining us for another edition of the Building Your Career podcast live stream, brought to you by Engineers with Ideas.